Okay, now we're gonna start a new topic, momentum and impulse. Okay, momentum and impulse, they are different than work and energy, but the relation between them is very similar to that between work and energy. And then the reason we study them again is because they're useful, right? They're useful in real life. And then there's also a fundamental law on the momentum and impulse. That's why we want to study them. These two concepts can be new to some people only because we use these two words less than work and energy. Okay, but again, they're going to be things we define in physics. Everything has a definition in physics. So let's take a look at the definition of momentum and impulse. So this is a PowerPoint 12, a new PowerPoint. Why do we define momentum? We want to define something in physics that indicates how difficult it is to stop an object, okay? A moving object, right? We know that if you want to stop an object, it totally depends on there are a few things you need to consider if you want to stop an object. You want to figure out how hard it is to stop an object. Let's use the following question, okay, to help us figure out what factors we need to consider if we want to stop an object. So take a look at that question. I hope this is intuitive, okay. Out of these four objects, moving objects, which one is the hardest to stop, okay? Even if you don't know any physics, I believe this is intuitive, right? So take a look at these four guys. Which one is the hardest to stop? I'm sure that everyone is gonna answer A, a 4,000 kilogram truck traveling at 50 miles per hour. Why do you think this is the hardest to stop out of these four objects? Well, you would say, most people would say, well, first of all, if you compare, there's only a truck and car, actually here, two objects moving at different velocities. If you compare the truck and the truck has a larger mass, okay? And then if you compare the two velocities we have in these four options, we actually only have 50 miles per hour and then 20 miles per hour. So 50 miles per hour is faster than 20 miles per hour. Okay, so intuitively I know that the combination of this larger mass and this larger velocity is going to be the hardest to stop. Right? So the truck, 4,000 kilogram truck traveling at 50 miles per hour is definitely going to be the hardest to stop out of these four objects. So, okay, so what did we learn from this question? What we learned is this. If I want to consider how hard it is to stop an object, there are two factors you need to consider, right? The mass, of course, and also the velocity, right? For example, if I have a tennis ball like this, even if it's moving at very fast, okay, I can still catch it. I can still stop it, right? But a car traveling even with a very small speed, well, that's also hard to stop. I'm not going to try to stop a car even it's moving at a very low speed, right? So there are two things you need to consider if you want to say, want to decide or want to compare how hard it is to stop different objects, mass and velocity. So two things you need to consider. You can't just consider mass or velocity. You need to take both of them into account. So in physics, we always define things to help us describe that, right? We don't want to use words, right? If I want to describe how fast something is moving, what do we use? We don't just use words. If we use words, how many words can we use, right? We're gonna run out of words very soon, like fast, slow, very fast, very slow, right? How many words do you have? And that's all quantitative. But if I use velocity, right? I calculate the velocity. I can show you the number. I can definitely compare the velocity, how fast something is moving between all kinds of objects, right? I don't need to use words to describe how fast an object is, how to compare this object with that object, right? All I need to do is just calculate the velocity using the definition. Definition is distance over time. So anything moving at 5 meters per second is definitely faster than anything moving at 4.9 meters per second. Okay? Even though it's hard for me to tell by watching them, but if I know these two numbers, I know how to compare them, right? Very easy. So we don't use words, we define something and then we get a number using the definition. So we just compare these numbers. So we want to do the same thing here. I want to define something to describe how hard it is to stop an object. And I just figured that two factors are important. You need to consider two factors, mass and velocity. So the simplest definition you can come up with would just be, well, why don't we just multiply these two numbers, right? If I multiply mass and velocity and if I want to compare how hard it is to stop an object, I just calculate the mass times the velocity for each object I have, and I just compare this product. So that's what we do in physics, right? So we define this thing mass times velocity. So that's something I want to use to describe how hard it is to stop an object, to compare how hard it is to stop different objects. And then I don't want to say mass times velocity all the time, right? And because this is something I'm going to use a lot in physics, so why don't we give it a name? How do we call them? Well, let's call it momentum. Okay, so we pick a word, okay, from our life. And then we just decide, let's call this thing we define momentum. Why? Because when we use momentum, okay, in real life, we say something has a large momentum. Well, that means it's hard to stop, right? Because when I was growing up, okay, the news would always say, Chicago Bulls have a lot of momentum this year. They may win the title again. That means it's going to be hard to stop Chicago Bulls because they have Michael Jordan, right? The greatest of all time. So we just decide, physicists just decide, okay, I want to call it something. So this thing we define, it's a little bit similar to the word momentum we use in everyday life. So why don't we just call it momentum? Okay, so the name just stays. So it actually doesn't matter what you call it, right? You can call it a different thing. The definition doesn't change, right? So we just decide to call it momentum, okay? So the definition is mass times velocity, so the unit is going to be kilograms times meters per second, right? So we're just going to call it kilograms per meters per second. We're not going to give it a new name, okay? So, but it should be careful, momentum, because it's defined in mass times velocity. So velocity it's a vector, so momentum you define, it's also a vector. So we use a symbol P for momentum. That's a symbol we use, usually people use for momentum. All right, so when you work with momentum, you should be very careful because it has direction. It's a vector. Every time you work with vector, you should be extremely careful. You should always pay attention to its direction. Now let's see how we define impulse. Now, okay, I just figured that if I want to describe how hard it is to stop an object, I need to consider mass and velocity. Now, what if I do want to stop anything? If I want to stop anything, I'm just changing its momentum, because I just defined momentum. If I want to stop something, I just want to change the momentum from some value to 0. Right? So if you want to change the momentum of anything, if you want to stop anything, okay, so what factors do you need? What do you need? Okay? Of course, you need to have a force to stop anything, right? For example, on a surface, if something is moving, the friction may be the force to stop it. If something runs into the wall has a force on this object, that's the reason it stops. So if you want to stop something, you always need to have a force, of course, okay? Common sense. Now, but how large this force is needed to stop an object, okay? If you think about it, you can stop something with a small force or large force, right? For example, the same thing moving on a surface, It can be stopped by the friction from the surface, okay? Very gently. It can also be stopped if it runs into a wall. It's going to stop very soon, okay? Very abruptly. So it's going to stop at the end. But in these two cases, the force is different. That's because the time is different, right? So think about this. When you're driving, okay, then you want to stop your car. The first case is this. You see a stop sign. You want to stop your car. Well, you're going to hit the brakes gently. You're going to let the car coast until it reaches the stop sign. Then it's going to stop there, okay? Because you have a fairly long time to react. What if you're driving, you see a squirrel jumps to the road in front of a car, or even a deer, okay? Well, you're going to stop the car as soon as possible. You don't have that much time to react. You're going to hit the brakes as hard as you can. Right? You're not going to do anything gentle, okay? Because you don't have much time. So, okay, if I want to change the momentum of anything, or if I want to stop anything, I need a force. But the amount of force I apply to stop this object actually can change. Totally depends on how much time I have, right? So, and then the general rule is that the shorter the time I have, the larger the force I need to stop this object, right? Okay. All right. So I just figured that if I want to stop an object, I need a force, but the force also is related to the time. Right? So I need to consider these two factors if I want to stop an object. So they are related. So again, I don't want to always describe things in words. I don't always want to figure things out based on our experience. Let's define something so that I can always use that thing to stop an object. Okay? And that thing must have both force and time in it. Okay? And that thing can also help me figure out how much force I need to stop an object. So the simplest definition is going to be, well, why don't we multiply these two numbers? Because I just figured out in order to stop an object, you're going to consider these two factors. And these two factors, they're going to affect each other. Right? The shorter the time is, the larger the force needed. So why don't I define something as force times time when you are stopping something, right? And then, okay, because we use this a lot, and I don't want to say force times time all the time, right? I decide to call it something. I decide to give it a name. What is the name physicists decided to give it? Impulse, okay? And the symbol we use is the I, which is the first letter of this name, impulse, all right? So this is another thing we define in physics. What is the unit of this guy? That's easy to see. It's going to be newtons times seconds, right? And then you can show that, okay, this is actually equivalent to kilograms times meters per second. Why? Because if you remember, what is the definition of newtons? We actually define that using the Newton's second law. So 1 Newton equals kilograms times meters per second squared. And then if you multiply that by seconds, what do you get? You get kilograms times meters per second squared times another second. This is going to cancel one part of this. You get kilograms times meters over second. So these two units, they are totally equivalent. If they have the same units, there must be some connection between them, right? They may be equivalent to each other. It's pretty much like the work and energy we discussed, right? Work and all energies, because they have the same unit, so they can be converted to each other. They're totally connected. So this impulse, and we know they're connected, right? So impulse is something needed to stop an object, to change the momentum of any object. And then, again, impulse is defined as force times time. So impulse is also a vector because force is a vector. So both of them are vectors. You should be extremely careful when you work with vectors. And then this is the definition for constant force, right? So if you do force times time, then this number, what do you use this number? Well, if the force is changing, you can't just use this, right? What number do you use if the force is changing? If the force is changing, we have a general definition. We just integrate the force over time, right? So that's how we define impulse if it's a varying force. So this is a more general definition for impulse, okay? So it's true for any force. If the force becomes a constant, you integrate that over time, you just get force times time, right? Because you just take this force outside this integral. And then if you make a force time graph, so the impulse is just going to be the integral of force over time. That's just going to be the area under the curve. That's what we learned in calculus. All right, so that's the definition of these two guys, okay? So you can actually show that if you start with the Newton's second law, okay? You can show that if there are many forces on an object, so the net force is going to be equal to mass times acceleration. If you start with Newton's second law, you can show that. You do some algebra. We're not going to do that here. You don't just do algebra, you can do some calculus. At the end, you can show that using these two definitions, you can show that this is equivalent to Newton's second law. You can derive this using Newton's second law, and you will get, if something is moving and the momentum is changing, so the net impulse from the outside, it's going to be always equal to changing momentum, okay? So these two laws, they're actually equivalent to each other. You can say this is a conclusion from Newton's second law, or you can also say Newton's second law is a conclusion from this law. And this we call it impulse momentum theorem, okay? So it doesn't matter how you call it, right? Even if you don't remember this name of this theory, okay? That's fine. But that's the connection between them. And again, think about it, right? The impulse is what we define to change momentum. So this makes sense to me, right? The net impulse on an object equals the change in momentum, right? That is the reason we define impulse. And then if you compare that with the relation between energy and work, right? If something is doing work in an object, the energy of this object is going to change. And the change in the energy is going to be equal to the work from the outside, right? So that the relation between impulse and the momentum, they are the same actually as the relation between the work and energy. So impulse is the mechanical way of transferring momentum. You can think of it that way, okay? So in this part, the impulse is just the equivalent of work. And the momentum, you can think of it as a vector version, okay, equivalent of energy in this part. The difference is that work and energy, they're scalar, right? But impulse and momentum, they are vectors, okay? So that's just another view to think about the motion of any object, right? Okay? So now there are three ways you can think about the motion of something. It's accelerating because there's a net force on it. Or you can think of if the energy is changing because some force is doing work on it. Or you can think of as the momentum is changing because there's some impulse from the outside on this object. Okay? All right? So we didn't derive this. As I said, you can show that. So we didn't derive because I know that people don't like derivation, so I'm not going to derive it here. But we're just going to use a very simple example to confirm this theory, okay? To confirm this is true, okay? Let's just use a motion where the speed is changing, right? Because you need to have some change in momentum, and the mass of an object doesn't change, right? So I want to have a process where the velocity is changing, and the velocity is changing, so there's acceleration. Okay, what is the simplest motion that has an acceleration? Well, constant acceleration. And what is the most common constant acceleration in real life? Free fall. So let's use free fall to verify this theory. Okay. Now let's take a look at the question on slide 6. So that's what we want to do. We're going to find the impulse in a free fall. We're going to also find the change in momentum in a free fall. And we're going to compare these two numbers, see if this checks out. So the first part, I want you to calculate the impulse from gravity on this stone when it's dropped from rest at a height of 2.5 meters. All right. If I want to find the impulse from gravity in this process, first of all, the problem should say explicitly, you want to find the impulse from which force, because there may be many forces on this object. It's like if the problem says, I want you to find the work. Okay, the problem must specify which force I want to calculate. You want me to calculate the work from this force or that force or the net force, okay? Because each force does different work on it. This problem, it says, I want you to calculate the impulse from gravity on this stone. And then that's the only force on it, right, actually. So now let's do that. If I want to calculate the impulse has a definition, okay? Even if these two things are totally new to you, you've never seen these two concepts before, that's fine. If that's something defined in physics, I'm just going to use the definition to calculate this thing whenever I want to calculate it. So I want to calculate the impulse in this process, so I just need the force and the time. The force is just going to be the gravity of this thing. So I have the mass of this object, so okay. So the impulse of gravity is going to be gravity times the time. And I do have the mass, so I just need to find the time. How do I find the time? The problem says the stone is dropped from rest at a height of 2.5 meters. So I'm just going to use this free fall. This is 2.5 meters to find the falling time for this process. And how do I find the time? I'm going to use one of the kinematic equations, because the first and the second equations have the timing. So you can pick one of them. And which one is going to be the best one? Because I know the height, so the second equation is going to be the best. The second equation is this, right? YF equals YI plus VYI delta T plus 1/2 AY delta T squared. So this equation has time. This equation also has this initial and final height. I do have this height, right? So I can call the final height, because that's the ground, 0. And then the initial height is just going to be 2.5 meters, right? So initial velocity, 0, because it's dropped from rest. And then what is the acceleration? 9.8 meters per second squared down. Okay, how do you tell the equation you're plugging an acceleration down? You call it negative. All right, so now you can plug all the numbers in, find the time, multiply them together. That's going to be the impulse. Okay, you can pause the video and finish the algebra. What is the number you got? So first of all, let's find the time, right? So the final height is 0, initial height is 2.5 meters. This is 0, and then acceleration is negative 9.8. I plug in, right? So this time I found it's gonna be 0.714 seconds. Now you can plug it into the definition of impulse. Multiply them together. What do you get? That's going to be 24.5 newtons times meters, or newtons times seconds. That is the impulse from gravity on this stone. Now let's do this. Let's calculate the change in momentum. So in order to calculate the change in momentum, I just need to calculate the final momentum when it reaches ground, right? So, because the initial momentum, what is the initial momentum of this stone when it's dropped from rest? That's going to be 0, right? Because initial speed is 0. I don't even need to calculate that. So let's calculate this P final. It's going to be m times V final. So the mass is given. How do I calculate this V final? Again, this is free fall. You can just use one of the kinematic equations. So now you have the time, so you can either do the first equation or the third equation. Either one is going to help you find the final speed. All right? So once you have the final speed, you multiply them together, you get the momentum. Okay, you can pause the video, finish the algebra. So if I find the speed, so if I want to use the first equation, I would get this. Vyi plus ay theta t, right? And the initial velocity is 0, acceleration is down, negative 9.8, right? You plug all the numbers in, you get 7 meters, negative 7 meters per second. So the magnitude of this guy is just going to be 7. And then if you multiply this by the mass, what do you get? So that's just going to be negative 24.5 kilograms times meters per second. The negative sign is just telling you it's down. The value is going to be 24.5. Now let's see. Then what is the change in momentum in this process? It's going to be P final minus P initial. So that's still going to be negative 24.5 kilograms times meters per second down, right? Or you can say the value is this, then the direction is down, okay? The value is 24.5. What is the impulse? The impulse in this case from gravity, and that's going to be the net impulse, right? Because the only force on it is gravity. So what is the impulse? It's 24.5 newtons times second. Impulse also has a definition, has a direction. What is the direction of this impulse? What is the direction of the force, right? You see, it's force times time. The force of gravity is down. So if you want to use a sign to represent the direction, you should also call it a negative. But anyway, changing momentum, the value I calculate, 24.5 down. Impulse, net impulse I calculated, 24.5 down. They have the same units, they have the same number, so that's a check. So the impulse, net impulse, it's going to be equal to changing momentum in any process. Okay? So if you want to derive this, you can do that by using Newton's second law. Okay? But we just checked it in a very specific example, free fall. So this is a general theory. In any process, if the momentum of something is changing, the velocity of something is changing, you will always get these two numbers equal. Net impulse equals change in momentum. So that's a theory. So why is this theory useful? Okay, why do we want to study this? We already know I can use conservation of energy, right? I learned I can use Newton's laws and kinematic equations. I can also use conservation of energy. We also learned conservation of energy. That's also a very powerful theory, very powerful tool. Why do we want to learn another theory? The reason is that momentum and impulse, they're very, very useful in collisions. Why? Let's take a look at collisions. So what is the features of a collision? Usually the collision in real life, it's going to be the time period, it's going to be very short usually, right? The collision happens really quick. And the force is usually not a constant. Actually, the force is it's going to go up and reach the top and then drops. Why? Let's take a look at the collision between a tennis ball and the racket in the next slide. That's pretty much like what happens when two things collide, and then what's happening in microscopic scale. So it's always true. Take a look at the collision between them. The tennis ball is going to collide with a string. All the strings on the bracket. So it's going to just stretch all the strings, right? When it stretches these strings, so the strings, they are elastic. So they're going to have a force trying to push this tennis ball in the opposite direction because they want to go back to their original length. So, but then as this collision happens, the tennis ball is going to stretch these strings more and more, so the force is going to get larger and larger because they are elastic. That's Hooke's law. So at some point, the tennis ball is going to stop. because the force gets larger and larger, so it's going to decelerate this tennis ball. The tennis ball stops, so that's the maximum displacement for all these strings. Right? And then after that point, the tennis ball is going to change the direction. It's going to turn around because the force is still on it, and then it's going to start to move in the opposite direction, so it's going to leave this racket until it has completely lost contact with the racket, so all these strings are back to their original size. So the collision has finished. But the collision usually happens really quick, right? So it's going to be a very short amount of time for collision, usually in real life, and the force is going to be like a triangle, right? So you take a look at the next slide, slide 10. If you want to draw the force, you will draw almost a triangle, right? So we call this impulsive force. So it's not going to be a constant force. It's going to rise to the peak really quick, and then it's going to drop to zero really quick. Okay? So that's usually how the force behaves in a collision, right? Take a look at these images on this slide. Hope they can cheer you up. Average dribble, okay? When Michael Jordan is dribbling the basketball, average dribble is just a collision between the basketball and the floor, right? And then you take a look at this graph. This graph is just actually a force, the behavior of the force between the basketball and the floor. And you can see the force, first of all, the collision happens actually in milliseconds. So it's really short. Right? Average dribble is going to be only like a few milliseconds. Secondly, the force can rise to a very large amount very large amount. So it can reach about 300 pounds, the force. Okay, and then you see that it's going to reach 300 pounds in a few milliseconds, and then it's going to also drop to zero. So it happens really quick. So for this kind of process, first of all, we can see that we're going to see. If I want you to estimate the average force in this collision, that's usually very hard, right? If I want you to measure this force in a collision, well, that's usually very hard because we don't have very good device to measure force. Secondly, the force is always changing, so it's really hard, okay? So that's one reason we want to use impulse momentum. What you can do is this. You can use this impulse momentum theorem. You can rearrange this equation, and then you can find expression, very nice expression for the average force in this process. So we can still use this theory to estimate the average force in this process, even though the force is changing. Right? Sometimes I want to know the average force in this process, so I have an idea how large this force is in this process. So we can use impulse momentum to help us do that, right? Because the acceleration is not a constant in this process. If you want to use the Newton's second law, it's a little bit hard to do. How do we use the momentum and impulse theorem to calculate an average force in this process? Let's take a look at it. What is the definition of impulse if I manipulate this equation? Well, if I manipulate this equation, the left-hand side is going to be net force times time equals change in momentum. And then remember this, if it's a real collision, the force is not going to be constant, right? So actually what you do is going to be this. This is what you really should do. You integrate the force over time, you get the change in momentum. But we can still say that there's an average force in this process. If I multiply the average force by the time, I should get the momentum, change in momentum, right? So if I divide both sides by the time, I actually get the average net force. So that's how we use this theorem to find the average force in the process, right? You can just divide the change in momentum by the change in time. Why is this useful? Because, as I said, measuring a force in the process is usually very hard. It's actually very hard to measure a force in the collision directly, because the collision only happens in milliseconds, okay? But the right-hand side, you see that we can measure these things very easily. We do have very good devices to measure the changing momentum, changing time. Changing time, well, you just use a watch, right? And you can use a very accurate watch. You can even measure like the time difference, like even smaller than milliseconds, okay? So we do have a very good device to measure time. What about this? This is mass times velocity, right? Momentum. So the mass of any object, easy to measure. You can put it on a scale. The velocity, we also have a very good device to measure velocity in real life. So instead of measuring a force in the collision, we can measure the things on the right and then divide them to help us estimate the average force in the collision. So that's the use of this, that's one use of this theorem. Now, again, it's always easier to understand a theory in a real problem. So let's take a look at the problems in slide 11. For a top player, a tennis ball may leave the racket on one serve with a speed of 55 meters per second, okay? If the ball has a mass of 0.06 kilograms, it's in contact with the racket for about 4 milliseconds. I want to estimate the average force from the racket on the ball. So if I want to estimate the average force from the racket on the ball, I can use this theory. I can rearrange this theory, get this, and then all I need to do is just calculate the changing momentum of the tennis ball and then the time for this collision. I can find the average force, estimate the average force. The time of the collision is given, 4 milliseconds. So all I need to do is just calculate changing momentum in this process. How do I calculate changing momentum? Changing momentum also has a definition, right? If you want to calculate changing momentum, you just do final minus initial. You just get to final minus initial. How do I find the final and initial momentum? Use the mass. The mass is the same. You just need to find the final speed and the initial speed. So what is the final speed and the initial speed in this process? The player is serving the ball. When the player serves the ball, it starts from 0, right? The ball starts from 0, and the player is just going to hit the ball with the racket really hard. And then it's going to give it a speed 55 meters per second. So in this case, the initial speed is 0, the final speed is 55 meters per second. Now you see that I have all the numbers on the right. I can go ahead and find the changing momentum, changing time, divide them to estimate the average force from the racket on the ball, okay? Now you can pause the video and then finish the algebra. All right, so that's that. Now let's see. If you use all the numbers you get, the mass of the tennis ball is 0.06 kilograms, right? And the time given is 4 milliseconds. You convert it to seconds. And then what is the average force? Average net force on it, it's going to be 825 newtons. So this is actually a very large force, right? 800 newtons, okay? And this is definitely a parameter, very important parameter, because when the manufacturers, they make this racket, they're going to make sure the strings, they're going to make some good strings. So this string, they're going to take a force, they can take a force that large in a tennis game, right? So that's a parameter they need to know. That's a parameter they need to know. How do they get the parameter? You can't measure the force directly in collision, but you can always measure the things on the right very easily because we have good devices to measure them, and then use the theory to help you calculate, to estimate the average force in this collision, okay? All right, so that's this question. Now let's take a look at the next one. As I said, momentum and impulse, they are vectors. they are vectors. When you work with vectors, you should be extremely careful because they have directions. You should draw them out, okay, and use that directions to help you to figure out how you manipulate them. Let's take a look at the next question. So still the tennis ball moves toward the player at 30 meters per second. The player hits the ball with the racket and returns the ball at the same speed, 30 meters per second, right? So the ball comes in, the player hits it back, so that's what happens. So the ball is in contact with the racket for about 5 milliseconds. What is the average force from the racket on the ball? I still want to do this. I still want to estimate the force from the racket on the ball. So I'm going to still start from this theory, rearrange that. This is how I'm going to calculate the average force, right? Changing momentum divided by changing time. And then changing momentum is always going to be final minus initial. But in this case, this is what happens, right? So this is a racket. The ball comes in with 30 meters per second. The player is going to hit the ball, and then he's going to return the ball with the same speed, but in the opposite direction, of course, right? That's how the tennis ball is played. It's played, right? He's going to return the ball to the opponent. Now, if I want to find changing momentum, I should do final minus initial. So, and then the final initial, how do I calculate? I just need the final and initial speed, right? What is the final initial speed? Now they are in opposite directions. How do I distinguish all different directions in an equation with vectors? I assign them signs, right? I'm not going to plug in 30 meters per second to the left, 30 meters per second to the right. I can't do that with the equations. I can't tell the equations, okay, this is a number to the left, this is a number to the right. You plug them in, you give me the answer. You have to give them signs, right? So you're going to decide the positive direction and negative direction here. Then you can get the right values and the signs for the initial and final speed, right? Remember, that's how we distinguish different directions, okay? If they're vectors, we're going to call one direction positive, then anything opposite to that direction, I'm going to kind of call it negative. That's how I'm going to distinguish the different directions with vectors. Then I'm going to repeat the same process. I will get the average force in this collision. Okay, now you can pause the video, finish the algebra. All right, let's see. In this case, again, you can pick either one as your positive direction. It doesn't really matter, right? You will get the same answer. You may just get a positive or negative sign, but again, if you stick with the positive direction you defined, you will always get the same direction for the final answer. Okay, so in this case, why don't we call V final positive? So this is my positive direction. Say this is my positive axis. So the final speed I plug in should be positive 30 meters per second. Initial speed I plug in, negative 30 meters per second. Why? It's to the left. How do I tell the equation that I'm plugging a velocity to the left, and then I have another velocity to the right? I call this negative, this positive, if I define positive in that direction. So if you plug them in, right, that's how you find the MVF minus MVI. And then you plug them in, you can, the mass is still the same, right? The time is 5 milliseconds. Now you put everything in this equation, what is the average net force? 720 newtons, okay. All right, so because you need to assign them the same sign. Think about it. If you don't assign them signs, you will get this number equal to this number. You subtract them, you get a 0. You divide 0 by some number, you get a 0. Then you will tell me, okay, in this process, the average force from the racket on the ball is 0. Does it even make sense? Okay, think about it. The player hits the ball with the racket really hard. I'm asking you to calculate the average force from the racket on the ball. You tell me your answer is 0. You're telling me the racket doesn't have any force on the ball. It doesn't make any sense, right? So you should always make sense of your answer. If you get a 0, you must have done something wrong because you didn't assign them the correct sign, because they are moving in opposite directions, they are vectors. Okay, you see that if you don't assign them correct signs, you're not going to get the right answer. Okay, you're not going to get the right answer. Okay, so when you work with vectors, momentum, and impulse, they are vectors. You should be always careful. You should always watch their directions, draw them out, assign them the correct signs, then you can get the right answer. Okay, so I'm going to stop here for this video.